So I'm Saaketh Narayan. Today, I'm just going to talk a little bit how our open source streaming dataset enables fast, scalable, distributed training. So yeah, so I guess this is just what we're going to talk about. Go through these four, and then hopefully we'll have some time for Q&A at the end. Cool. So streaming dataset is a PyTorch iterable dataset. It is purpose-built for fast distributed training, and it makes basically streaming your data from cloud storage as fast and cheap and easy as possible. So some examples of how we've been able to train with streaming as well as our customers are, we've been able to scale with streaming to thousands of GPUs. DBRX, for example, was trained on more than 3,000 GPUs and is a 132 billion parameter model. We've also internally used huge data sets, like hundreds of terabytes, and streaming has performed well on all of these across many data modalities and many model types. So why is streaming needed? So without streaming, there's a bunch of challenges that you see, especially related to your data. And model training, honestly, is oftentimes blocked by data challenges. So without streaming, you have, your data can't be ingested by your models. Your training is slowed down because of data loader bottlenecks. You can't combine multiple data sources. Training resumption becomes very hard, et cetera. And with streaming, as you can see, I'm not going to go through all these, but we've been able to successfully address a lot of these challenges. So one thing we really focus on is getting the most throughput out of your training, out of your data loading. So on the left here, you see an example of having really bad throughput. So at sporadic intervals during your training process, you'll be data loader bottlenecked, and you'll see like frequent throughput drops, just like on the left. If you really have good throughput, you should see something like on the right. The second thing here is data mixing and shuffling. So in this example, we have a bunch of data sources, so C4, GitHub, and like an internal data set. Streaming lets you just create stream objects over these data sources, specify some sort of proportion, and seamlessly mix these data sets during your training. Another feature that is really important to us is elastically deterministic training. So with streaming dataset, as you see on the top, you get fully deterministic loss curves whether you use 1, 8, 16, 32, or 64 GPUs. This is really important because it lets you automatically scale whatever runs you did at small scale to very large GPU scales. Even in the middle of training, you can just take your run on 32 GPUs, say, and scale it up to 128, and you will get deterministic resumption every single time. So here's another example of where deterministic resumption comes into play. If I have data that's stored among many cloud providers, then I can just continue this training run. Let's say I have an OCI failure or something. I want to train from S3. Then I can just resume my training run straight from S3 with the same data set. So how does this all work? The first step is you need to convert your data into a streaming dataset ingestible format. And the second thing is there's some mechanisms that happen during training that sort of enable all these features that I just talked about. So the first step is dataset conversion. So you take your raw dataset samples, shown here in gray. Let's say they're like a CSV file, whatever you want, and you pass these through MDS writer objects. So what these do is these serialize your raw dataset samples into binary using these MDS writer objects and write out row-oriented mosaic data shards. So that's shown here in blue. Basically, each shard has your serialized sample as well as a header that describes where to seek to access that particular sample. So, for example, I'll write out maybe an image, and it'll say, okay, image 3 is at byte, let's say 500, and we can very easily, very quickly just access the sample in the header and then seek to where that sample lives in the shard. And that allows for really fast, low latency random sample access. During training, what happens is we store, basically, you can store all of your data sets or data sources in the cloud. And so here we have 2 data sources or streams. Each one of them has a bunch of shards as well as an associated index.json file. So this index.json file describes all of your sample data set metadata. So for example, how many shards are in there? How many samples are in each shard? How many bytes do I expect from each sample? Stuff like that. And when the streaming dataset is initialized, these index.json files are downloaded so we have an idea of what exactly your data is composed of. Then we deterministically partition your samples among nodes, GPUs, and data loader workers. So here's a sort of minimized view of this. My total sample space is composed of samples across these two data sources. So that's shown here in blue and in green. I'm training on 2 nodes, each with 8 GPUs. So I want to split up all of these samples across workers, nodes, and GPUs such that when I increase my number of nodes, this partitioning stays the same. So what this allows me to do is basically I need to maintain the invariant that each global batch, regardless of the number of nodes or GPUs or workers I'm using, is composed of the same number of samples. Not just the same number of samples, but the same sample IDs. So we make sure that this partitioning is deterministic, and then we can also apply some partial shuffling algorithms that are going to take the samples that are assigned to each node and distribute them among the nodes such that your dataset egress costs are still minimized, so you still have the same sample IDs and shards assigned to each node, but you have really good shuffle quality. So this enables a lot of different things that you can see in our documentation, such as different batching methods, various different shuffles, and we've done a lot of work to make sure that these partial shuffles are equivalent in quality and model conversions to like fully shuffling your data, which if you're trying to download shards is highly inefficient. So during training, what happens is your data lives in cloud storage, so each data loader worker is assigned some portion of the sample partition tensor. And data loader workers check if the shard that contains the sample that they need is present on disk. And if it's not, they go ahead and download it. And this happens sort of preemptively. This happens ahead of time, and we're able to prefetch shards. The shards are downloaded from the cloud, and then because of the row-oriented, very low latency MDS format, we're able to just very quickly retrieve these samples. Each data loader worker retrieves these samples from the shards that are on disk and loads them into GPU for training. So yeah, that's sort of an overview of streaming. And yeah, we'd love to field any questions from you guys. Thank you.